All right. Good morning, everybody. I'll let people file in real quick. They're coming in. All right, quick poll before we start. How many people know about fuzzing? How many people who have developed a fuzzer? Okay. How many people know about genetic algorithms? 2 in the back. Awesome. All right, 3. So feel free, we'll dig in anywhere you want to dig into this talk. This is actually part of a larger talk that goes about 2 hours. So this is like the 30-minute synopsis of everything. So we're going to hit the high points. Topic today, fuzzing, what, why, how do fuzzing, and actually how you mix together genetic algorithms and fuzzing. So first off, who am I? This is the first time I've been in the Asheville security community. The picture is hilarious. That's why I put it up there. That's actually, I was on a panel, and I guess they thought that was a good picture to put up. So it kind of looks like I'm making out with the camera. It may have been. I am a principal engineer at Cisco Systems. I've been at Cisco for about 10 years, which is kind of odd for me to believe that I've been there 10 years now. I was a penetration tester in our Advanced Security Initiatives group. We were responsible for hacking all of Cisco products to figure out where the vulnerabilities are at before other people on the outside do. So that's about 20% of my time now. The majority of my focus now is a security researcher in the Advanced Security Research Group. We do outreach with universities. So we publish RFPs, requests for proposals, in multiple different areas that we're interested in, namely right now threat mitigation, analytics, privacy, and advanced crypto. And then we go through the funding process, give them money, and we work alongside them. So that's the majority of my time now. And I do IT admin and monitoring for a small enclave inside of Cisco. So I don't do the larger Cisco, but I do ASIG's enclave because we have different security requirements because we are hacking Cisco products. So I do some monitoring there, and I love beer. Some other things that I've been doing, I was the lead organizer for Bsides Knoxville. So if you guys haven't made it out to Bsides Knoxville, we're going to do it again next year. We had about 200 people come out last time around. Awesome event. I'm also lead organizer for the Cisco's Offensive Summit, where we bring all the penetration testers from Cisco to one location, and they share their tools, techniques, and practices. I mentioned this because we're moving to a model where it's going to be kind of like Blue Hat. So if you're interested in that, talk to me. We're going to try to bring some external researchers in so that you guys can mingle and see what we're doing. Done big data analytics stuff. I've done continuous security assessment for virtualized assets and DevOps stuff as well. So basically, they just call me to do random stuff all the time.
Just a quick comment.
Yeah.
I want your job because it looks like you can drink while working.
Yes, I do sometimes.
The whole time.
Yeah.
Yes, I can.
Also, we are hiring. We are always hiring. Our office is about 60 in Knoxville. We do internships. Yeah. We do internships for college students, and we also have full-time positions. And our internships, as discussed yesterday, are hands-on. We don't treat them like second-class citizens. We sit them down next to a penetration tester on a product, and they are expected to learn and find vulnerabilities and report them out to BUs. So, yep. And we do CTF stuff. We do the whole gamut. So it's fun. It's a great place to work. So first off, I shouldn't have done that. God. You got me off track. Fuzzing, can anybody define fuzzing? Yeah, I know. God, we already cheated. I'll give it to you. So this is the academic approach to fuzzing. Everybody, when you think about fuzzing, they just pull off their favorite tool, this open source, they just start running it. They don't really think about what's happening under the hood. And there's actually this kind of categorization of fuzzers that you can have that tells you what the fuzzer can actually do and what its methodology is under the hood. So we're going to walk through all that. But fuzzing in general, systematically sending random or deliberately malformed data, that's the key there. You're sending just garbage, right? Either it's just random, random, or you're actually choosing specific values to send in. And you're going to any of the program's input vectors, whether that be file processing, network data, so anything like that. You're looking to identify implementation errors, your typical buffer overflows, which are becoming less common these days, use after freeze, double freeze, all that good stuff. So pretty simple here. You got a program. You got some anomalous input to try to set fire to the program. You may have some analysis that you're going to be doing either programmatically, or you're going to have the engineer actually go through all the logs and figure out what happened and figure out why it was vulnerable and why it crashed. And then hopefully that gives you a good program in the end, right? So that's the 1,000-foot view of what fuzzing actually is. But it's kind of more complicated. Questions on the fuzzing? Good? Fuzzers are not going to find all software defects, right? You can't. You just can't do it. Some corporations think that I'm just going to buy Codenomicon, I'm going to run against my product, and all of a sudden I have a secure product. Doesn't work that way. It's a combination of fuzzers will get you closer to a secure program, but you're going to have methodology put into your software development lifecycle to make sure that your developers know how to code correctly and eliminate errors, plus your testing cycles are going to have to account for trying to find vulnerabilities as well. So it's basically, it takes a village to birth a secure program, right? Another view of this, you've got a fuzzer, right? A monkey just slamming on a typewriter, sending anomalous data in there. It's generating a bunch of test cases, and you can see the gamut here. A lot of them are just files. Some of it are network traffic. Some of it's Bluetooth. Some of it's command line arguments to programs. And you've got a system under test. And so a lot of people think that, okay, the big three here, you've got Microsoft, you've got Linux, you've got Apple, but I'm in the Cisco world, right? I've got embedded systems and I've got anything under the sun. So you're looking at our routers and switches, you're looking at our cloud services, right? How they handle APIs, is there command injection in there, is there XSS? And I'm also looking at things like IP phones, right? Who could have their own real-time operating system, or they could be using Linux under the shelf. It just depends. Cisco just tends to use anything and everything. And what you're trying to do is with Fuzzer is partition this big set into two different sets. One, which is the normal files that pass and are handled, right? Even if they're anomalous, the program actually catches the errors and exits normally. Or you've got this other set that crashes everything, and you want to find all of those in the larger set. So fuzzing you think about as a search space problem. Here's your search space. And here's the set that you actually want to find, right? So this is setting us up for how to do genetic algorithms and fuzzing. Questions? Cool. Yeah?
Yeah, at some point when you talk about, wanted to see the mic move.
Yeah, that's good. Cool.
Will you talk some point about your view of fuzzing in a security context versus, say, program robustness?
Yeah.
You know, there's some kind of overlap and stuff, and not to get too pedantic about it.
Yeah.
I always look at this more as a robustness thing.
Yeah, it can be a robustness thing, but when we're getting ready to go through the different types of fuzzers, I'll hit on that for you, because there is a layer that you can put above everything where fuzzing just tries to find crashes and malicious behavior, or anomalous behavior, right, of the program. You can put a layer on top of it to figure out, was the crash actually something that was a security problem, right? And so I'll show you in that layer where that can lie. Three different types of fuzzers. The first type here is a mutation fuzzer, and this is the original one. Fuzzing was developed by a professor at the University of Wisconsin-Madison. His name was Barton Miller, right, in the 80s. And it was by accident. Like every good invention, it's by accident. He was remotely dialed into a computer, and it was during a thunderstorm. Thunderstorm put some interference into his connection, crashed the program on the other side. He's like, oh, this is cool. Can I make this happen more often? So he then, like a good professor, turned that into an assignment for his students and made his students figure it out, right? From there, it's been an ongoing assignment, and he actually publishes reports on the robustness of different applications, whether it be on Unix or Linux or Mac OS X. So they do that periodically. But in the literature about fuzzing, nobody really goes through these different layers and what makes a good fuzzer. So I'm going to walk through them really quickly so we get to the genetics. At the bottom, attack heuristics. What type of anomalous data are you actually sending to the program? You can think of this as random, or you can think of it as more targeted. Are you looking at the bounds of an integer, right, for wraparound? Then on top of that, you have to think about how you're actually executing the program under text. So I call that an executor, right? Are you just going to spawn it? How are you going to deliver the test case to the program? Are you going to do dynamic binary instrumentation to monitor execution, or GDB, anything like that? From there, you have to be able to actually determine if the program crashed. So health monitoring, how are you going to do that? Are you going to send periodic pings to the program to see if it's still up? Or are you just going to watch it to see if it exits normally? The other thing after you go for health monitoring is you need to make sure that everything's reproducible. So you have to do some sort of logging to figure out what test case caused the crash, because you're doing thousands upon thousands of test cases. What if one crashes at number 100 and you don't stop until 50,000 and you don't have that record? You can't figure out which one actually did it. So logging is there. Something that I added in when I was doing research in this area is a reporter. So I like to have on-demand summarizations where I don't have to look through all the logs, but I can just ping the fuzzer and say, what's up, what's your current status, what's all the results, and it can tell me that. So I view that as a reporter. And then when you're talking about security problems and how you differentiate between just something that is just bad behavior of the program or a crash that is actually exploitable, this is where you can get to the classifier. And that's an optional component that you'll see on some fuzzers built in, others just won't have it at all. But there are programs like Bang Exploitable or Crash Wrangler who will take the stack trace and then figure out, did your program actually control any of the registers, which would then make it exploitable. All right, so that's how you can move from the fuzzer just being something that tests robustness to something that is security-based, right? Questions on mutations? Cool. The next step up, after a while, people figured out, whoa, that's two. People figured out the mutation fuzzers, they don't have a lot of smarts in them, right? You're just sending a bunch of random data and programs are crashing. But what if you have code that you have to get past certain checks to be able to get deeper into the program structure, right? You can think about packets that have TLVs in them. If you change the value field and you don't change the length, you might never get down past the length check to find out more parsing errors, right? So Dave Attell from Immunity, I think it's Immunity, in 2002 wrote a paper on the advantages of block-based modeling. And the whole gist of it is, let's take a modeler and let's embed it into this whole stack. And so what you're going to do is you're going to describe the data format and where to put the anomalous data and pinpoint in there. And you can walk the data model and then determine, this fuzzer can actually determine where to put what attack heuristics into what area. So it adds the smarts in it. Again, the classifier in this situation and all situations is optional. So that's the improvement from the 80s to 2002. Examples of this, the big one that everybody knows is Peach, right? Peach gives you an XML API where you can actually define the data models. Questions? Okay. The last one and the newest in this area is actually a feedback fuzzer. So this is adding in some type of search algorithm, whether that be something like constraint solving or concac execution or genetic algorithms to be able to search the space for different inputs. One of the big fuzzers in this area is Microsoft's Sage fuzzer, where they have a distributed fuzzing farm across all of the engineers' computers, right? When they're not using it, it uses extra cycles, and they do constraint solving on their programs to find different code paths to go down to try to test. So it's kind of a twist there. Again, you can or cannot add a modeler in this situation, and the classifier is optional as well. So, and we're going to focus on this space when we mix together fuzzing and genetic algorithms. Questions on the categories of fuzzers? Cool. All right. So the big question, we got this guy again, and we have some genetics. How are we going to turn into this guy, right? So what we're going to do is we're going to use a bunch of different tools to be able to add genetic algorithms into the fuzzing process. We're going to use some dynamic binary instrumentation, or you can actually do this through a scriptable debugger interface like LLVM, or LLDB, sorry. And we're actually going to use some static analysis techniques with IDA Pro to actually help us derive attributes to affect our evolution. So, simple genetic algorithm. There was, what, 3 or 4 people who knew genetic algorithms? So real quickly, you start out with a population. So you can think about this as just candidate solutions to a problem. And there's tens, hundreds of these. And you'll go through and in some way, shape, or form, you will evaluate the fitness. How well are they actually solving your problem, right? Then based on their fitness, you'll actually go through and they will reproduce and create a new population. So when we talk about reproduction, we talk about selection. How are you going to select the fittest candidate solutions? out of your population. There are multiple ways to do that, like random selection or roulette wheel, where you think about just spinning a roulette wheel, or you can weight the different elements in the population. Then once you have the parents actually selected to breed a new candidate solution, you have to talk about two genetic operators here, crossover and mutation. How are you going to select where in the particular gene, or chromosome, sorry, what gene you're going to cross over to create the new? And I'm going to go into these more in detail next slide so you can see it. From there, you can talk about mutation. How are you going to randomly alter parts of the new child that you're making? You can think about this as inserting your attack heuristics into a particular file or a new child. And these two are governed by some probabilities that we may or may not talk about. So, genetic operators. Selection, very straightforward here. I have a huge population. I choose two parents who will then breed to create a new child for my new population. So I've chosen X and Y here. Then we talked about a little bit of crossover. So this chromosome has multiple genes in it, and you can cross it over, or you can choose multiple points in the chromosome to actually take genes from each one. So we've randomly selected the middle, and we take part of the first parent and then part of the second parent, and then that gives us kind of our intermediate child. From there, we go to our mutation scheme, and this is, do we randomly flip any bits in the new intermediate child? And you can see with a probability, we've chosen this gene to actually change, and this gene to actually change. So after this whole process, this gets me a member of a population, and you do this to generate the number of members the number of elements in the population that you started with, right? So it totally replaces the new one, and then you just keep going in a cycle. So that's kind of the whole very quick spiel about genetic algorithms. We didn't really talk about the probability of crossover mutation, but we can if you'd like. But basically, whole scheme, you go through, you get the new population, it goes in, it's the population again, then you go through fitness evaluation, reproduction, and then you just keep going, either until you set a limit to say this is the number of generations that I want to I want to go forward, or you actually have a solution to your problem that you think is approximate to what you want. So, questions on genetic algorithms? That was really quick. Good? All right.
I actually have a question.
Yeah.
So obviously, most people probably learn this through like the game of life.
Yep.
And there's lots of fun ways to solve that. When it comes to fuzzers, I guess my question is, how would that work, especially if you're talking about random data versus random data that matches a pattern? Like it is an address. It is an email, except it's a little wonky in a way that might pass the validation, but have exploit payload at the end of the line or something. Like I'm not quite sure I follow how you would set up a parent-child, like a genetic algorithm to generate that sort of data.
Great question. And this is part of this research, is how do you bring those two together? So I love the question. The research that I did here is in file-based fuzzing, right? So you can think about your population as a bunch of files. We'll choose a target. Let's say we're going after Mac OS X's preview software, right? So I'm going to seed my initial population with a bunch of random PDFs that I find all over the internet, right? I don't know if they're good or not. I'm just going to start out with that. From there, I'm going to run them against the program, and I'm going to figure out how well they do from whatever measurement of well, and we're going to talk about that later on down through. They'll get some scoring, and then I will have them reproduce. And so when I have them reproduce, we'll actually choose a point in the file to take them and cross them over. And I'll take half of one file and half of another one, slam it together, right? And then that gives me this intermediate child. And then from the next one, I choose, do I want to put any type of special attack heuristic in here? Do I want to insert random data somewhere in there, or do I not, right? And you can actually be smarter than that and choose particular values that you care about. You can also go above and beyond and have a model of what a PDF file actually looks like, and then take this intermediate child, match it up with the model, parse it out, and then from the parsing you could actually choose a particular place in the file to put stuff in, right? So you're trying to get further and further down different code paths that way. That answer your question?
Yeah.
Cool.
Thank you.
Part of this too is I was seeing how lazy I could actually be and see if I could have the genetic algorithm evolve new test cases and me not have to worry about it, right? So a lot of the research I did was just insert anomalous data as a mutation. I was. I know how this works. Let the computer do work for you. So we've kind of hand waved, like I've got a fuzzer, it'll do genetic stuff. We'll measure it and say, we'll measure each test case and say how well it did based on some measurement. How does that all work, right? And this is the crux here. How we're going to do this is we're going to go through a couple of different phases. The first, our program under test, we're going to do some static analysis before we even start fuzzing to do what I call attribute extraction. So we're going to take something that's on Linux, Mac, or Windows, one of those programs, shoot it to IDA Pro, right? Because IDA Pro can offload and do all that work for us, and it'll break it down. So it's going from like a black box technique. We're assuming no access to code whatsoever, right? So that's a key here as well. It disassembles it, puts it in some nice control flow graphs for me. It can calculate some different attributes about each function for me. And so I can run some IDA Python scripts against IDA Pro to pull out attributes at the function level or at the program level. At the function level, I can look at like the number of local variables that they're allocated for that particular function, the size of those local variables. I can look at the number of arguments that function that takes. I can look at something called Cyclomatic Complexity, which we'll talk about in a few. And then we can actually look at how complex the function actually is based on the number of assembly instructions that function has. Okay? So this one kind of gets the length of the function. This gets, are they jumping around a lot in the function, making F checks and such. So we've got attributes about a program now. Okay, that gets us one step further. How do we mix that with what's actually happening when I run a test case? And to do that, we're going to use dynamic analysis. And we're going to, for each negative test case that I run, I'm going to record the hit tracing information. So record where what it's executing in the program, which functions actually get touched by that negative test case. We'll use, you can use this with a scriptable debugger like LLDB, or you can do something with dynamic binary instrumentation. One of the big ones there is Valgrind to watch execution as it happens. Which, you know, over here, there's your dynamic binary instrumentation. Here are your debuggers that you can actually use, GDB. But okay, I know what functions were executed in the program per negative test case. I've got attributes, but how do I bring those two together, right, to get a scoring for each negative test case? Well, what we can do is we can define a variable set representing all those function attributes that we derive from the static analysis. Then we can use those variables and create mathematical functions based on those to let us define fitness functions for our genetic algorithm. Then for each negative test case, we can do some fitness evaluation by looking at the dynamic and the static analysis and sum or average those variables of all the functions that were actually executed. We good? That's the crux. We got it? Cool. So examples of fitness function variables. And these are just some that I just threw out there that you could do. We talked about the number of locals and arguments. We've talked about the size of locals. You can also do like the function stack frame size, cyclomatic complexity. And so you can take these modifiers up here and put them against those variables. And so you can do like A would be the average of the number of function arguments for all the functions that were executed, right? And then you can actually look at some of these other variables that not necessarily will mean anything when you do a sum or an average over them. And you can do like how long did the program execute, right, as a measurement. Because maybe you wanted the program to take longer in processing your input because you're using dynamic binary instrumentation and it needs 60 seconds as opposed to 40 seconds to get to a particular area of the code, right? Path uniqueness is the code path that test case is taking unique over the whole set of negative test cases that you've ran. And you can actually look at code coverage. Is this something new that I've executed that I've never executed before? So some examples here of mathematical equations that you can use, BA times R. So you're looking at the average number of local variables and recording longer execution time. You're looking at the average cyclomatic complexity with the GA. BA divided by V and BA times V are just spins on the same notion of looking at the average number of local variables and either punishing or rewarding code coverage. And just at a variable, an illustration of some of the simple ones, where I'm getting from B and D, right, the size and number of locals, A and C, the size and number of the local arguments, and F, the whole stack size for that actually frame. And so it's key to note here, depending on your ABI, some of these may or may not mean anything, right? So if you're going from an x86 to an x86 64, arguments wouldn't be passed on the stack, so you wouldn't be able to calculate them correctly. The size and number, so that might not mean anything in a 64-bit program. So these can change as your ABI actually changes. Questions? Cool. Cyclomatic complexity. So how complex is the function that you're actually executing? Just think about it as a directed graph, right? You've got a bunch of nodes, which you can think about the if conditionals that get broken out to different jumps. So the nodes in this point will be the basic assembly blocks there, and the edges are going to be the control transfer instructions between those different assembly basic blocks, right? You can take the formula that was developed by Thomas McCabe, straightforward. And there's a star for this because that's still up to debate, right? Some people say that cyclomatic complexity greater than 10, meaning there are probably more than 10 transfers in that particular function, tends to mean more defects because the coder is not factoring out their code into other functions and making it simpler and honing in on that particular functionality. It may or may not be the case, right? So you can play with this this measurement and see. So there's a bunch of papers on whether that is or isn't true, but something to try. Execution path uniqueness. This variable is based off of building transition matrices between all the basic blocks in a program, and you record execution, and then you do your basic counting of how many times did it go down this path, how many times did it go down that path, and then you can multiply out for each test case all the paths that it took, and then get a score to say, was this unique or not based on the transition matrix. Okay, Markov chains, high level. Good? Yeah.
So in your... So the way you're doing this on the executables.
Yep.
Have you considered, or why aren't you using source code analysis? Clearly, for some of the things you're talking about, analysis is not available.
Yeah.
But I would think for a lot of, say, Cisco's products, you would have access to that.
Yep. I'm doing it black box style because I want to crash Mac programs. That's basically it, right? There is good research on doing this from a white box perspective, and when you do that, if you have access to the compilation tool chain, then you can instrument the program, right? Mm-hmm. A lot of people don't have access to that, right? So people who are doing vulnerability discovery for common platforms like Mac or Windows, they don't have source code. So they need a way to be able to find vulnerabilities, and this would be a way to do it.
Yeah, but it's getting back to our industry, that's fun, and maybe if you're looking for bug bounties or something that's productive. But if you're actually trying to develop a product or a system, a web app or something, it would seem you'd want to do that to get the most leverage you could from.
Yep,
okay.
You were exactly correct. If you are in the situation where you do have source code, this is not the methodology to take, right? Okay. That can actually be seen with new fuzzers like AFL, American Fuzzy Lop, which actually, if you look at what you need to do, or the first release of it, further releases went to a black box style, but the first release of it actually altered the code as it was assembled. Right, and it actually created trampolines to be able to do accounting for which basic blocks you execute in a program. So very smart implementation. But yeah, if you have source code, there are better ways to do it. Okay. But if you're a hacker on the outside world, in the outside of that company, you got to go black box and you got to have a way to do it.
Okay, thanks.
Yeah. Any other questions? Cool. So overview now, simple GA, what will we do here? Wall of text, seed initial population, our chromosomes are files, their variable length. That's important because I learned the hard way that they can crawl to infinity and take up all of your hard disk space. So when we take one of these test cases, we evaluate it, we run the application under test with the negative test case, monitor execution, record the function calls. I used Valgrind for this when I did the initial research, and boy is that slow, and we'll talk about why. This is a lot faster, but it's still slow. So you can calculate the fitness based on the recording function calls, and then we just do our reproduction. We breed our next generation. We do selection, crossover, and mutation. I did the non-smart way of just inserting random data because I want to see how well genetic algorithms in general did with fuzzing, right? I can always make it smarter with better attack heuristics to target different failures of coding that people could do, right? Like integer wraparounds and all that stuff. And then one key here with this implementation, I actually used elitism, which means I just preserve the best solution, whichever best is when I deem my mathematical function, to stay in the population to go further. So we're going to focus on runtime. At the end, this actually netted about 30 to 35 vulnerabilities in preview. And this is kind of older, the work that's been done. So this was about 4 or 5 years ago when I did this. And some of those were exploitable, some of them weren't, but they should all be fixed. And one reason it's fun to go after preview is that Safari uses it for rendering those libraries underneath. And quick look, if the file is actually just on your desktop, quick look will automatically try to render it, and then you can just crash Finder over and over and over again. So that one is fun as well. So you can send a file over to somebody, they'll just download it, they'll put it on their desktop, they'll browse to it, and then all of a sudden they have stuff crashing. So it's fun. So runtime analysis, and this is looking at different population sizes and what's been happening. So the bottom is looking at a mutation and a generation fuzzer and how long it takes for them to execute a test case. It's somewhere between 3 and 6 seconds on average. Then you go up here, and all of these are genetic algorithms with dynamic binary instrumentation. They're variations on a theme, different types of genetics. As you can see, it's horrible. It's like 40 seconds a run, right? You're going to be waiting a lifetime to get results in this situation. And also what's cool about this is you can see this graph going all the way down and getting closer and closer to one single point. That's actually the files merging towards one solution, right? So that's a problem that you got to factor in as well. So at the end, it's like the same file being run over and over again. And that's the purpose of this CHCGA, which we're not talking about today, but it's a cool little algorithm if you look at that. So we've got to combat the runtime problem. And the simplest way to do that is distribute everything, right? So we can take a look at Amdahl's law, which basically means let's make the common case fast and let's do an evaluation of the genetic algorithm to see what's happening here. So if we look and we see that the genetic algorithms are taking 0.5% of the time for me to breed new samples, okay? What's really taken the longest is this chromosome fitness evaluation, and that's because I'm running everything with Valgrind. So imagine running preview with Valgrind, right, and then waiting for a result. So I need to speed up this portion of it, right? So how do I do that? Well, I can do some math based on this function, and I can say if I actually just add 4 more nodes to this cluster and I distribute this chromosome fitness evaluation, I can actually pull my test case execution time down to 7.36 seconds, right? Really fast. And I can scale into whatever number I want, right? So I can build a cluster very easily here. So how do we do this? Well, we can do what's called a master-slave GA parallelization, where I do fitness evaluation independent. So on multiple computers, they're going to be running preview. They're going to then report back their results to the master, who will then, once all the results are collected, go ahead and breed a new population, seed it back out to all the slaves to then run it again to pull the data back in, and then it's just a continuous cycle here, right? So we're using a synchronous model because I need to wait for fitness evaluation of all the chromosomes before applying any of the genetic operators there. Questions on distributed algorithm? Pretty straightforward. There's a cool graphic of what it could look like. So you've got your workers, you've got your organizer, your master, and so the things that I need to worry about at this point are how do I distribute the files in some sort of data store? How do I direct work, basic queuing? And then how do I distribute configurations, because I need to tell endpoints how to actually run what program and what program needs to be tested. So I deem that something called a distributor. And I'm actually looking at this from a SETI at home type of experiment. Can you just have people come up on a network and then start fuzzing, right? Can they just pull down your configuration files and then all of a sudden start running all your test cases and then contribute to a massive fuzzing cluster, right, with zero knowledge? So we talked about organizers, we talked about workers. Distributor, in the proof of concept code that I did, basically the fuzzer is configured through a YAML file that tells it how to execute the program and where the program should live and what operating system it is and a couple other niceties. You can tar that thing up, shoot it over through email to somebody or put it up on a website and let them pull it down. And then also in the actual distributor, in the configuration file, it has addresses for the queuing system, so how to hook up to the RabbitMQ system that I'm using. And for a data store, I'm actually using Mongodb, which actually has a cool feature called GridFS, where I can just start storing files in MongoDB, and somebody can just connect up to MongoDB and pull those test cases out with them. So it's pretty cool. Results then. There's where we were before. Here's where we are now. So we're getting closer, which is n equals 4. So dramatic speed up. Questions? I'm good. We're concluding. Questions on all this?
That's impressive, Jim.
Yeah. And that's just with 4, right? So we could scale it a lot. And that's with Valgrind. If you do LLDB, you get somewhere down in the 20s, I think, because I did just a real quick proof of that. And so then you think about distributing it then with LLDB, you're going to get way down, right? But about 5 years ago, technology wasn't to a point where you could do that reliably. So, conclusions. We didn't talk about vulnerabilities found, but got about 32 defects in preview. Didn't really apply it anywhere else because it was just a proof of concept to just see if it would actually work, right? Minimal set of negative test cases, so we only ran probably about 50,000 to 100,000 test cases through this thing and got that type of results. So it kind of leads me to believe that genetic operators are naturally good fuzz testing operations, especially looking at the crossover and mutation. As we just talked about, the parallelization, awesome. You can drastically improve execution time no matter how you're monitoring your execution. And then it's feasibly possible for us to match Peach and Mangle's per negative test case runtime if we add more workers to the distributed architecture. Future work that I've never gotten to, doing a custom debugger, doing some Python bindings to improve this hit tracing, which I think I was hinting at LLDB there. And then trampolines, which is highlighted because that's what AFL uses, right? They actually hook all the functions to then know what get executed, and then they do some scoring in a shared memory area so then they can pull it out later, right? So it's really quick. Introduce data modeling into this whole thing because I'm not using data modeling at all, so that would actually help me target particular areas of a PDF, which would help me improve the attack heuristics. And then there's some crazy ideas about comparative study of genetic operators and different algorithms out there because we did a simple GA, I also did a CHC GA, but there are multiple ones out there that you could apply to this problem. So. Questions? Yeah?
I thought it was a joke for a second, but the title of the slide.
What?
Read it.
Warp up? Yeah. This morning slides.
Totally cool. Yeah, that's why I said don't bother putting the screen.
It kind of works, you know.
So is this generating reporting that goes back to developers to say that we found this and we didn't find this, and what sort of reporting is going back? This looks like you're aggregating the failures and you're kind of saying, you know, how many did you find and what kind, but is it specific enough to go back to a developer to tell them what to fix?
Yeah, so this is in general a good question about fuzzers, right? The reporting mechanisms for fuzzers, for the most part, are not good consumption for developers. You have to be able to summarize it appropriately. When we reported these back to Apple, we actually gave them the example files that caused the crash, plus the stack traces, plus our analysis on what went wrong, right? And where we think the errors are in the parsing code. So that kind of gave them a general area to work on. So when you're doing fuzz testing, those are kind of the key elements that you need to give back to your development team, namely the crashing test so that they can reproduce it, and any report that any hints to what you think is wrong in the code, right? As well as any stack traces you may have so that they can run through and do it.
And hopefully the sample, the data that was used to crash.
Yeah, yep. Questions? Yeah.
Any idea from the output what the relative effectiveness would be in terms of finding problems using pure random changes versus the ones that are coming out of the genetic algorithm at this point?
No. So the two algorithms that I ran, Mangle and Peach, right? Mangle was the mutation fuzzer that just did randomness, right? Peach was the data model, right? And I used a very basic data model. And I ran them for the same number of test cases so that I could kind of factor in and see is genetics actually working. And they came out pretty well, right? Now, I attribute Peach not finding a lot of errors. I definitely found more errors with the genetic algorithm, but I attribute Peach not finding more errors based on the data model that I had, right? And so that's something you need to factor in when you're choosing a fuzzer. If you go with something like an intelligent fuzzer like Peach, where you have to do a data model, there's a lot of time that you have to spend to specify the data format, right? And that may or may not ever be complete, all right? So.
Well, and that's one of the benefits of the genetic algorithms is that you get to the point where you're not dependent upon the same developers who probably wrote the code in the first place, making the same mistakes describing the data as they did writing the code that ingests the data.
Yeah, yeah. Any other questions? Cool. Thanks, guys.